Okay, let's try to finish up the lesson from, wasn't yesterday. What was yesterday? From Wednesday. And let's see. There he goes. All right, and I believe we left off right before function. All right, so we've talked about relations already in that first lesson. So today we are going to talk about what a function is. Shh, I hear talking. Let's pay attention. Come on, I've started. I've given us enough time to talk before, so now is the time to listen. All right, so let's write down. I don't usually write down full definitions, but I think we use functions so often that I think it's a good thing to do. Okay, so what is a function? It's a relation, right? We've talked about what relations are. Basically, kind of like ordered pairs, right? One thing related to another thing, an x and a y, if you will, in which each element, so write this down, in which each element of the domain. Now this definition, if you just read it, you're not going to say, oh, okay, I know what a function is then. It might not be quite so easy. Is paired with. So a relation, you had pairings, but this is a special kind of a pairing. Is paired with exactly, and that's important, exactly one element in the range. One element in the range. Now, if you just read that, or if I read it to you, probably wouldn't make much sense at all to you, but that's what we're going to do here. So I'm going to show you by an example what this definition really means. Because a lot of times seeing an example kind of makes the definition come to life a little bit. So after we do the example, then we'll look back at the definition of a function, and it should make a little bit more sense to us after we see a little bit of an example. So we're going to do quite a few things. This is like the most basic one. So I'm going to give you 3 ordered pairs in this example. All right, so let's go back to the definition again, and let's take a look at it, and let's put it into like layman's terms, okay, regular people talk. It says, it's a relation in which each element of the domain. So which ones are the domains, these 3 ordered pairs? What's the domain? The x, okay? Yeah, it's the -3, the 4, the 2, exactly, all right? Sometimes it's helpful writing them out like this. You don't have to. This one's pretty easy. Don't really need it, but let's just do it. I'll show you why. So it says each element of the domain is paired with exactly one element in the range. So exactly, meaning, or exactly one element in the range. So no more than one. So not 2. So each of the domains is only paired with a unique y value. So the x is paired with a y value. So we've got -3, 0. We got 4, -2. We got 2, -6. So look at that -3. What is that paired with? It's the 0. Okay. Is -3 paired with anything else here? No, because there's no other -3s, right? So the -3 is only paired with the 0. What about the 4? The 4 is paired with the -2. Are there any other 4s that could be paired, or with another range? There's not. There's no other 4s. That's the only 4. And what about this one, the 2? What's that paired with? A -6. So each domain, each x, is paired with exactly one y. Would you agree with that? What if I threw another one in here? What if I said 2, 7? So that 2 would be paired with a -6, but the 2 would also be paired with a what? A 7. Is this domain paired with exactly one range? One element in the range? No, it's paired with 2 of them, isn't it? All right. So all 4 of these would not be a function, right? But the 3 that we started with, is that considered to be a function? Yes. all right, because each element of the domain, each x, is paired with one and only one value in the y of the y's. Okay? Does that make sense? Let's do another one. It's kind of what I did when I stuck this on here, but this is in the book, so we might as well put this here as well. So it's 4, -2. Write these down. 4, 2, 9, -3, -9, +3. Actually, let's make this a -3. In the book, it's +3, but I want to show you something because this could be a little confusing. It really is not going to make any difference on our answer, but sometimes people get confused on this. So what are we looking at? We are looking, I'm not going to list them like this. I guess you could if you wanted to. Let's take a look at it. This 4 is paired with what? A -2. But then you got another 4, don't you? That's paired with a different number. So is that 4 paired with only one element of the y's? It's paired with 2 of them, isn't it? So one, or if you have a repeat, okay, that's kind of an easy way to look at it. If you have a repeat in the domain and it's paired with something different, then this is not a function. So right here, what's my answer to this? This, yes, it's a function. What's my answer here? No, it's not a function. Why? I don't even have to look at the other stuff, okay? If these two right here make it not a function, it doesn't matter if the other ones make it a function or not.
So if there's a repeat, it's not a function
It's,
at all?
well, if there's a repeat in the x values, okay? If the x values are repeated, then it's not going to be. Now, watch. When I say that, I should say this. When the x's are repeated and one goes to one number and the other one goes to a different number, like I could have 2 4 -2's here for whatever reason, then it would be okay. And that would be right here. Watch this. This 9 goes to -3, but this -9, which is a different number, right, still goes to -3, but that's fine. That could be a function because they're different domains. They're different x's. They're not the same. So you can have different x's go into the same y, okay, but it could still be a function. Make sense? Let me show you graphically what this means. Now, I could graph these, and let's go ahead and do that. Let's graph the first one. Let's just put little x and y axis here. When I say graph these are super easy to graph because they're just points, right? So all we're doing is just putting points on a number line. I'm not even going to be all that accurate with this. Let's put this in a different color. All right, -3, 0. Where's -3, 0? About right there. Would you agree? 4, -2. There's 4, -2 would be about right here. And then 2, -6. 2, -6 would be about right there. Okay? So we can look at a graph visually and determine if it's a function or not. So really, if you have one x only going to one y, we have it here, we have it here, we have it here, that's a function. Let's throw this one in here. Remember what I said this was? 2, 7, right there. Now, just looking at this visually, I can look at it. I don't even have to know what the numbers are. I can look at this right here. If I know that this is at 2, and that goes to a certain number, and that goes to a certain number, right? That's at 2. Look, that point right there and that point there are right on top of each other. Do you see it? Mm-hmm. So I could, if I wanted to, and I do, drop a vertical line. Let's push this over just a tad. There we go. Okay? So if I can draw a vertical line and it's going to hit 2 points, that automatically tells me that this is not a function. Did we do this in Algebra 2? Yeah. Okay, did we? Okay. It's called the vertical line test. Remember that? Yeah, this is usually something you would do in Algebra 2. I just can't remember exactly if we did it or not. But it's called the vertical line test. So if the vertical line test crosses more than 1 point, if it crosses 2 or more, then it's not a function. Okay? So let's do a couple other. I won't even put the graph thing there. What if I had a graph? Oh, that's the wrong thing. Here we go. What if I had a graph? Let's not even do that one yet. What if I had just a graph like that? All right, there's a line. It's diagonal. It's just a straight line. Is that a function? Yeah, it is a function. How can you test if it's a function or not? What's that? What is it? Oh, I got passes up here if you have to go to the bathroom. Oops. All right. So does this pass the vertical line test? Yeah, I could put a vertical line. Let's make it vertical. There we go. Watch. I could take this vertical line and put it anywhere here. Is it ever going to hit 2 points on that line? No, it'll never hit 2 points on that line. So is that line a function? Yeah, absolutely. All right. Everybody with me on that? Okay. Let me just move that over. All right, let's do another type of graph. What if you had a graph like this? Oh, thank you. Oh, wow, you put the sticker on there and everything. Oh, that's perfect. Thanks. That's awesome. That's for my grandson for the game tonight. He's coming. I can't wait. I won't be able to see him much because I'll be taking pictures. But all right, is this thing? This is a parabola. Did we do parabolas last year? I can't remember. Okay, I think we did. We might have. I taught a lot of math last year, so I can't remember what I did in each class. So here we go. Watch this. Is this a function? Is a parabola like this a function? Yeah, here's my vertical line. I'm going to test it. Will it hit 2 points anywhere here? Anywhere here? Here, 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 here? Nope, never. It'll never hit 2 points, will it, on that particular graph? All right? Let's do a weird graph that I know we did not do last year. We didn't even do it in pre-calculus last year. That's called a parabola. This is called a hyperbola. Something like that. It's kind of like a parabola, just kind of 90 degrees, kind of sideways. Now, is that a function? No, it's not a function. Why? Because if I put a vertical line here, it's going to hit at 2 points, isn't it? All right? So that is definitely not a function. All right? Let's do a few more just for fun. And we're going to be doing a lot of these graphs. We're going to be graphing them ourselves. What if you had a weird looking graph like this? This is a cubic function. So like x cubed. Okay, that's what that would look like. Is x cubed a, oh, come on. There we go. Is x cubed a function? Yeah, because everywhere you put that vertical line, you'll never hit it twice. Okay? I'll show you one more. I know you're probably thinking, okay, Mr. Hammer, I got the idea. But I'm going to show you another one anyway. We're eventually going to be doing graphs like this. Like that. Look at that. That's like a sine or cosine graph. We call them a sinusoid. All right, it's kind of a funny word, but we'll be graphing stuff like that when we start doing some trig in here. All right, is that a function? Yep. Everywhere on here, it only hits at 1 point. Okay? You get the idea? So vertical line test. Yep, pretty easy, pretty basic. Oh, here, let's do this one. Remember how we did the inequality stuff last year and we had to shade certain portions? All right, so let's do something like that. Go different. Oops, I don't want that to be green. Let's click off of it. Come on, click. There we go. All right, what if we had a graph that looked something like this, and then this is all shaded in? We did that last year, didn't we? Yeah. All right. If it's greater than less than inequalities, we shaded it in. Is that a function? We said before just a straight line was a function. Yes, it is a function, but is this a function? No, because anywhere on here, remember the shaded in represents all points on there. So it's definitely hitting more than 2 points or 2 or more points, okay? So this is not a function. So the inequalities here are not functions, okay? All right, enough of that. I think we got that settled, don't you? Yep. All right, let's go to something different. And this is something, again, that I told you yesterday or the other day, first day class, that we are going to repeat quite a few things that you guys did in Algebra 2, especially early on. All right, so this is something that we've done before. And we're talking about functions. So let's talk about a different notation for functions. Back in algebra, especially Algebra 1, you did a lot of this kind of stuff. You did evaluate, I don't know, let's just think of something easy, 2x plus 1 if x is equal to, I don't know, 3. Remember that kind of stuff? Yeah, you might have done that even in pre-algebra, I don't know, at least Algebra 1. Okay, this is where you learn this kind of thing right here. So what did you do with this? If x is equal to 3, you just replaced that x with a 3. Let's just do it really easy. I know it's super simple. That's 6 plus 1 is 7. There you go. But now we're going to do basically the same kind of thing, but the notation is going to look a little different. Okay, this is called function notation. So instead of saying evaluate this if x equals 3, here's another way you could do it. Well, we're going to, this notation is this. Probably remember that from last year, don't you? How do we say that? If I was going to say that out loud, it's f of x. That's right. Okay, so we would say f of x. All right. That's how we say it. It's not f times x. F is not a variable. F is just used to represent a function. Now, you don't have to use f. It's very common, very, very common to go f of x, probably the most common. But you could also go g of x is very common as well. H of x is common. Literally, you could use any letters for that function. You don't have to use the f. Why do you think they use the f in the first place? Probably for function. That's my guess anyway. I don't know for sure, but my guess is they use f because it stands for function. But you could have different functions. Like if you had different equations, 3 different equations, one would be the f of x equation, the other one would be the g of x, the other would be the h of x. Make sense? If you had 3 separate equations. So it doesn't matter. You don't even, it doesn't always have to be x, all right? It could be another letter, but these are the most common. F of x, g of x, h of x, they're the most common that you're going to see. So let's rewrite this with the function notation instead of if x equals 3. Instead of doing that, here's what they would do. They'd still probably put the word evaluate in front of it, but they're going to say evaluate f of x equals Actually, what they would tell you, let me think. What they would probably do is tell you this. They would just tell you this thing, f of x equals 2x plus 1, and they're going to say evaluate f of 3. All right, so that's what they're going to do. So here's your little formula, your little equation. All right. And they're just going to say evaluate f of 3. Instead of saying if x equals 3, this is what they're going to tell you. They're just going to say find. A lot of times they might say find. They might say evaluate. Sometimes they might say find f of 3. It's telling you to do the same exact thing. So what does this mean? It means, look what we did. We replaced that x with a what? With a 3. So what are we going to replace this x with? A 3. So it's the same exact math. It's just the notation. It's just the look of it is a little different. That 6 plus 1 is 7. You get the same answer. No biggie. Okay? We did a lot of that last year. You're probably very familiar with it. But beginning of school year, we got to be reminded of a lot of stuff. So that's what we're trying to do. Okay? Yeah, we got a little time. I'll do this one. So let's do an example. In the book, it's example 6. And it says, find f of negative 4 if f of x is equal to. It's exactly what we just finished doing. It's just a little bit more complicated, that's all. But the idea is exactly the same. All right? So what if you had a problem like this? What would you do? It says find f of negative 4. Well, here's what your f of x function is. So what do we do with that negative 4? Just throw it in every time you see what? See an x, that's right. Okay? So let's rewrite it. So what is f of negative 4 then? So f of negative 4 equals 3 times negative 4 cubed minus 7 times negative 4 squared minus 2 times negative 4. I'll just save you the work on this. You work it all out. I'm not here to show you that part. You should be able to do that yourself. And then it comes out to that, and you're good to go. All right? This is the part that's important for today. It's just replacing the x with a negative 4. Very simple. Wouldn't you agree? Yeah, I think so. All right. There's a part B to that. I'll skip that. Let's go to the next part right here. It's kind of the same thing. It's a little bit weirder. That's why they put it in a different example. So right here, we're just putting numbers in for x. But look at this one. This one's a little weird. It says find h of a. This time they don't put a number in there. All right, they put a. But a represents a number. Okay, that's what we're doing. If h of x equals, and then this big crazy thing, 3x to the 7th minus 10a to the 4th plus 3x minus 11. All right, here we go. It looks a little complicated because you got something to the 7th power. I don't like taking stuff to the 7th power, but this is actually a lot easier because that's not actual, well, it is a number. It's a variable, but we don't actually have to figure it out math-wise, do we? We don't have to like do the arithmetic with this. So what are we doing? We're replacing this x with what? With just an a. That's all we're doing. All right. So it's not a. I hate to say actual number because it does represent a number, but we'll just say it that way. You know what I mean, right? It's not a 2 or a 3 or a negative 7 or something like that. All right. So we just take wherever we see an x. Oops, I meant that. That's supposed to be an x right there. Sorry. So all we do is replace the x with an a. So this is super easy. So it's just 3a to the 7th minus 10a to the 4th plus 3a, just minus 11. And there we go. Does that make sense? Yeah, so sometimes they'll have weird stuff. Sometimes they'll say find h of x minus 3. Now that would be horrible to do because you're going to have to take x minus 3 to the 7th power, and that's going to be super ugly. I wouldn't give you anything that complicated. But what would you do, though? How would you start it? You go 3 times what? X minus 3 to the 7th, and so on. Okay? All right. Again, they would not give you that x minus 3 to the 7th because that would take forever to do. All right, enough of that. Let's go on to one more thing, and then we'll be finished. How about that? Example 8. We're going to go back and talk about domain again. All right? Not even range with this one. We're just going to talk about the domain. So this is example 8. And it says, state the domain, I'll just write that down, of each of the following. State the domain. This is something you're going to do quite a bit, all right? So we kind of did the easy stuff just to kind of get you in the swing of things. This is the kind of stuff they're really going to ask you to do, all right? So let's see what we got. So we got a part A and a part B. That's what the A is. So here's my function. F of x equals x cubed plus 5x over x squared minus 4x. All right. What in the world are they asking you to do? Well, this is a graph. If we wanted to, we could take Desmos. Remember I told you about Desmos? Anybody look that up on there's an app with a Desmos app, all right? Did we use that last year? Yeah. Okay. All right. Yeah. So so I would do that if I were you. It's not a big file or anything. It's just a little app, but it's excuse me, it's powerful. It's really to me, it's one of the best graphing apps or programs that you can use. You can also get it on the computer as well. If you graph this, it will graph it, but we want to find out what is the domain? What are the possible x values for this function right here? Okay? I don't care about the y values. I just want to find the possible x values. So for instance, if I said something easy, y equals 2x plus 1, and if I was to graph this thing, We all know how to graph that, don't we? Now this one's be a lot more difficult to graph, and I'm not even going to graph it. But I just want to show you something just so we can have a visual. So 1 would be your y-intercept, then you rise 2, 1, 2, run 1. So that's what it would look like, wouldn't it? So I want to ask you what the domain of that would be. Kind of talked about this the first day. What's the domain of that red line right there? All the real numbers, everything. Okay, every x is a possibility, all right? Because if you look at this, are there any restrictions on this x? Is there any number you cannot put in for this? Some people say, well, you can't put a negative in there. Well, sure you can. You can go 2 times a negative number, can't you? And then add something to it, sure. You could put 0 in there, right? You could put a positive number in there, and you'll come out with an actual number, right? So you'll come out with an actual range, a y variable, or a y value. But what about this? For instance, what if I did this? Let's, again, make it a little easier than what it looks right now. What if I had, like, y equals 1 over x. Everybody look here. Could I have y equals 1 over x? Well, I shouldn't say can I have it. Of course you can have it. But can you put every single value for x in for that and you still get a number? No. What can you not put into it? A 0. You could put negative numbers in for x, right? Because you could get 1 over negative 2. It's fine, right? That's a number. Would you agree? You could put a positive number in there. You could put big numbers in there. You could even put fractions in for x. You can put decimals in for x. You'll still get a number. The only thing that you won't get a number with is if you put in what? A 0. Because x, in this situation, the denominator can never be 0. So x cannot be 0. Does that make sense? So, if you look up here, what can the denominator not be? It cannot be 0. What was that noise?
A desk.
A desk? So watch. So in order to find the domain, especially on a fraction, what you're going to do is take the denominator and you're going to set it so it's not equal to 0. So we want to find out. It can be any number at all except for whatever makes the denominator 0. Hear what I just said? Yep. Okay. So what we're going to do is we're going to actually set it equal to 0 and find which x's won't work. All right, we're trying to find the restriction. What x's are going to make this not work? Well, we got to do a little math. All right, it's basically algebra 1 math, algebra 2 as well, I guess. Oh, how do I solve for x here? What can I do? Well, it's got a not common denominator, but it's, see, what is it? They both have x in it, correct. So we're going to factor out an x, all right? A common factor, that's the word I was looking for.
What's the thing where it's like, is the special equation?
But this is not. This is not a difference of 2 squares because of this x. See, that x is not being squared. If it was x squared minus 4, then it would be a difference of 2 squares. But in this situation, you can only factor out an x. That's really the only way you can do this, okay? So, so you got, no, not really. Yeah. All right, so we factored out that common factor of x. And now, remember, when 2 things are being multiplied together and it equals 0, we set them both equal to 0. So I'm going to set this equal to 0. And I'm going to set this equal to 0. Do you remember that? Now, if I set this equal to 0, what's x? Add a 4 to both sides, x is 4. So now I put equals here, but really, those are the values that cannot equal 0. They can't be in here, okay? So I'm going to say x cannot be 0 and x cannot be 4. Because check it out. If I put a 4 in for this, what's 4 squared? 16 minus 4 times 4, which is a 16. 16 minus 16 is 0. So 4 does not work. So I can use any real number. Okay, so if I was going to write my answer, I could say they are all real numbers except for, there's other ways you could write this, I guess, but this is how I wrote it, except for what? 0 and 4. All right? So you can put any number in the world in for these x's except for 0 and except for 4. Because the top doesn't matter. What if we didn't have the denominator? Then what would the domain be for the top? It'd be all the real numbers, right? Because I could put any number in there I wanted. I could put a negative number in there. I could put a positive. I could put 0 in for the top, couldn't I? Because I would come out with a 0. And 0 is fine. It's a number. But I can't have the denominator come out to a 0. So I take the denominator and I say, oh, the denominator cannot equal 0. Now, I didn't put the not just because it was, I don't know, easier to see how to solve for x, okay? But technically, it's not equal to 0, okay? And so I come up with x, I come up with 0 and 4, so that's my domain. So that is my answer. Whoops, missed it a little bit, but that's my answer right there. Okay? They're not all going to have fractions in here. They might have other things. You might have a square root, right? So like, I don't know, can I do this in my head? Well, let's talk about this one. Okay, just a second. What if I had this? Can I put any number in for x?
No, you can't put a negative.
Can't put a negative. Can I put a 0 in? Yeah, because I can take the square root of 0. I can't take the square root of a negative number. So really, it's everything from 0, right? So x can be anything greater than what? Or equal to 0. So that would be my domain if you had something like that. So those are the two big things that they're going to do with this, okay, with restrictions. The restriction is usually in the denominator, and the restriction is usually in a square root, okay? Let me put the homework down, and then I'll take a question. We only got a couple minutes left, but... All right, so it's section 1.1. Make sure you put the section on your homework. Everybody hear me, especially people that haven't had me before. Put section 1.1 on your homework. It's pages 10 and 11. And you're doing 17 to 49 odds. Did some of you guys get started on this the other day? So now you should be able to finish it. Maybe you were able to finish it before because we've probably already gone over this in Algebra 2. But now, officially, you're only doing the odds, okay? So you don't have to do all of those. That's really not that many. Plus, I kind of split it up into 2 days a little bit. Yeah, and they shouldn't be that hard, okay?